We've just shown that all excess charge on a conductor must reside on its surface. Suppose we hollow out the solid spherical conductor from the last slide to obtain a spherical shell with inner radius r sub I and outer radius r sub O as shown. If we now place charge Q on the shell, where does it go? The arguments from the last slide can be repeated here to show that this charge must be uniformly distributed on the outer surface of the shell. Suppose we now place a point charge Q0 at the center of this spherical shell. What will happen to the charge on the conducting shell? Well, the charges on the conductor are certainly free to move. But what determines how they will move? We know the electric field in the conductor must be zero. Adding the point charge Q0 would create a non-zero field in the conducting shell. Therefore, the charges in the conducting shell must move so as to cancel the field produced by the point charge inside the shell. We can use Gauss's law to determine how the charge is distributed on the shell. Namely, we'll choose the Gaussian surface to be a sphere centered on the point charge with a radius between r sub I and r sub O as shown. Since the E field is zero at all points on the surface of the Gaussian sphere, we know the integral of E dot dA over the surface must be zero. Consequently, the charge enclosed by the Gaussian surface must also be zero. The charge enclosed is equal to Q0 plus the induced charge on the inner surface of the shell. Therefore, we know this induced charge must be equal to minus Q0. The spherical symmetry of the shell ensures that this charge will be distributed uniformly on the surface. Therefore, we can determine that this charge density, sigma sub I, must be equal to the total induced charge divided by the surface area of the inner surface of the shell. What about the outer surface of the shell? Well, we can determine sigma outer, the charge density on the outer surface of the shell, because we know that the total charge on the shell must be equal to Q. Therefore, the total charge on the outer shell is equal to the net charge Q minus the charge on the inner shell, which is minus Q0. Consequently, we determine the charge distribution on the outer surface to be equal to the total charge on the outer surface divided by the surface area of the outer shell. We'll now move on to an example with a different geometry.